Hey, rotational motion! What I'd like to do is introduce you to the new quantities immediately. Use the old ones. You're familiar with these. Displacement, velocity, and acceleration. The new ones. Angular displacement, angular velocity, angular acceleration. They're known as the rotational variables, okay? So the symbol for angular displacement is delta theta. The change in theta is the angular displacement. This figure over here is called omega. It's lowercase omega. It's a Greek letter. Looks kind of like a little buttocks, a little booty, but there we go. That's what it looks like. All right, angular velocity. Angular acceleration looks like a little fish. This is called alpha. So first letter in the Greek alphabet, alpha. And the units are radians, rads, because we need more rads, you know that. And radians per second, rads per second, rads per second squared for acceleration. And so there we go, those are the quantities. And so what I'm going to do next is kind of introduce them in context of what each of them really means, and then I'll show you the equations of rotational motion, which looks pretty darn familiar. Whew. And so here we have it, angular displacement, angular velocity, angular acceleration. Let's start with angular displacement. Delta theta is, well, the difference between theta and theta naught. Okay, what is theta? It's actually a ratio of two measurements. One of them is called the arc length. So if you take any kind of circle and just trace out one part of that circle, that's called the arc length. So the ratio of that arc length over the radius, which is of course the line from the edge to the center, gives you theta. So that's where the radian comes from. It's actually developed from a ratio of these two quantities over here. So arc length is known as S divided by R here, radius, gives you theta, all right? The convention is that the positive direction gives it counterclockwise rotation. So if I twist it like that, like this, okay, that is a counterclockwise rotation, and that would be positive, and therefore this way, on the golf disc, is a negative direction based on a convention. Now it's kind of arbitrary again, but that's what most people use. Positive is counterclockwise. So this angular displacement stuff is just how much something rotates, and if something rotates a full revolution, we call that the circumference, 2 pi times r. If it is any other rotation, it may be part of that circle, then it's determined by the angle theta, and the arc length, if you will, is theta times r. All we're doing here is solving for s. S is theta times r. That gives you your arc length. Okay, angular velocity here in terms of average angular velocity, that bar means average, and it's the change in theta over change in time. So it's a change in your angular displacement over change in time. Here we go, theta minus theta naught over t minus t naught. Looks familiar, looks exactly like velocity, except instead of x, we now have theta. Right? So what is it? It's the rate at which something rotates that it changes its angle. So how fast is it changing its angle with respect to time interval? And there's the time interval. Angular acceleration looks familiar too, right? All right. Average alpha angular acceleration is the change in angular velocity, omega over time, change in time. So it's omega minus omega naught over t minus t naught. Looks exactly like acceleration with velocity, except now we have angular velocity. So the patterns are totally the same, which is kind of cool. We can reuse the same patterns as before. The rate at which something changes its angular velocity, this is what, with respect to time interval, this is what angular acceleration is. That's it. So I'm going to show you the rotational equations of motion with constant alpha. So the only way they work is, just like last time, we need to have a constant acceleration in order to use those equations. Now we need a constant alpha. So here we go. And so here we have it, the equations of rotational motion at constant angular acceleration alpha. You should look super duper familiar. Wow, look at that. Okay, the patterns are totally the same. So we've got omega equals omega naught plus alpha t. Wow. Delta theta equals omega naught times t plus 1/2 alpha t squared. Same pattern, except we're just dealing with rotational variables. And number 3, which sadly is neglected by the AP1 equation sheet. I have no idea why. These two are there. This one is not, but it's important because you may need to use it. So I'm going to give it to you because, hey, if we have the other counterpart there, with the velocity and acceleration and displacement, we need it for angular as well. So here it is, omega squared equals omega naught squared plus 2 alpha times delta theta, okay? These are very, very familiar looking. The difference is that we need a kind of a Rosetta Stone, if you will, a translation between linear and angular variables. So here are the relationships between them. R is the radius measured in meters. Delta x, which is displacement, linear, is equal to delta theta times the radius. Pretty simple. So we looked at that before with the angle times the radius gives you the arc length, but that arc length is in terms of, if we think of this as rolling motion, so if this were on the ground and rolling like a wheel, then that would give us a delta x, not an arc length. V equals omega times r. Hey, we see a pattern here too. Simply, if you take the angular variables and multiply it times the radius, you're going to get the rolling counterpart. So it would translate in terms of the linear motion. And so there you have it. This is the Rosetta Stone. This is also not on the AP equation sheet, but it's very, very important to use if we want to go back and forth between the two, which we do. In fact, I'd like to show you a quick example involving a bicycle. So guys, here's the sitchy. We got a bicycle. Its wheels have a diameter of 0.7 meters. I said diameter. I did say diameter. It's definitely the diameter. And it starts from rest and moves with a constant angular acceleration alpha of 1.2 radians per second squared. How far does it go? How far does it roll? All right, that's what we want to know. How far will the bicycle have traveled during this time? Great phrasing, but there we have it. Here is the list of variables. We do the same technique that we've done all the time. We don't have to create this super duper chart because we're not dealing with 2 dimensions at the same time that we need to keep track of, just one, but we do need to translate them at the end. Delta x is what we want, we don't know it. Delta theta, I think we're gonna need, we don't know it either. Omega naught is 0 radians per second. Why? We started from rest. Boom, keywords, note them, use them. Omega, we don't know it. Okay. Alpha, we totally know it. 1.2 radians per second squared. And the time of travel, 25 seconds. We also know something, they told us the diameter was 0.7 meters, diameter of the wheel, but we want radius. Easy, divide by 2. So I just did that immediately. Radius is 0.35 meters. So what we got is, I started with delta x equals delta theta times r. That's the translation we need to make. We need to know delta theta in order to get this. We know the radius already, so let's find this, delta theta. So I need an equation of delta theta. I like the second one. Second one's gonna be good. Here's why. Delta theta is omega naught times t. Omega naught is 0 because of beginning from rest. Plus 1/2 alpha t squared. We have both of these, check, check. 1.2 radians per second squared and 25 seconds. So delta x is 1/2 r times alpha times t squared. All I did here was take this thing and substitute it in for delta theta, and so delta x is just this expression here. So it's a pretty easy thing to solve, and so I did. I plugged in the numbers after this was isolated, which it already was. So 1/2, 0.35 meters, 1.2 radians per second, 131.25 meters. That's how far it goes. So pretty simple example. So we'll be doing some activities in the lab and also some problems kind of similar to this to get used to working with these variables. Right on. So that's what it is. Morad, out.